I want to say a few things that will help you get the most out of this course. First of all, take notes. Just watching the videos is already pretty good, but that tends to lead to a kind of superficial knowledge, which means you might understand everything I'm saying in the lecture while you're watching it, but you might not remember it. A week later, there is a lot of empirical research backed by statistics showing that comprehension and memory are much better when taking notes by hand compared to taking notes on your computer. Second, pause the video a lot, like as often as you want. I will encourage you to pause the video throughout this course in order to think through an answer or work through an equation or write some code. I really want you to be engaged and active in the learning process. Now, I do try to make my lectures fun and engaging, but, this isn't passive entertainment. This is active learning, and I hope that you will help me teach you by staying engaged in the lectures. Third, a few things about the computer code in this course. Even if you are more interested in the theory and the intuition and the math and you're not really interested in the code per se, I still recommend watching the coding videos because there are concepts and issues that come up when implementing statistics on computers that you might not get just from looking at the slides. And so I talk about these kinds of implementation of practical details in more depth in the coding lectures. So you'll still get a lot out of the coding videos even if you're not following along with the code per se. Now, all the code videos are in both MATLAB and in Python, so you can use whichever language you're more comfortable with. Now, you definitely do not need to be an expert in either of these programming languages in order to do well in this course. However, I do not cover elementary beginner level programming skills. So if you are no experience whatsoever with MATLAB or Python, then you might want to take an intro-level coding course first and then come back to this course. Now, if you are comfortable with variables and for loops and basic plotting, then you'll be fine. I do take the time to explain the more advanced coding techniques that I'm using. So as long as you have some basic familiarity with coding, you're good to go. If you are familiar with both MATLAB and Python, then I recommend going through the course in MATLAB. MATLAB is a more comfortable environment for numerical processing and data visualization, and in my opinion, it's simply easier to follow along in MATLAB. However, you will need access to the statistics and machine learning toolbox for most of this course. The fourth thing I want to discuss is that if you already have some experience with statistics, then some of the topics in this course might already be familiar to you. Of course, you are free to skip any videos you like or watch them in any order, but I created this course to flow in a specific way. And so I do recommend going through the lectures in order just in case there are some new details that you might not be familiar with. Fortunately, on the Udemy video player, you can adjust the playback speed so you can actually set the videos to go at twice their normal speed. That's a good way to get through familiar material quickly. And of course, you can go back and slow down the video if there's something new. The last thing I want to mention here is that Udemy will ask you to leave a review of this course after only the first few lectures. Now, that's probably a little bit too early for you to feel confident about reading this course. So you should feel free to click on the Remind Me Later option. However, when you are ready to leave a rating for the course, then please do. It means a lot to me. I really appreciate it. It helps future students make a decision about whether they should enroll in this course. And it also helps to support me to make more courses for you in the future. I'd like to say a few quick words about using the code in this course before getting started. Now, as I wrote in the course landing page, you don't actually need to write a single line of code in order to successfully complete this course. It's totally fine. You can watch the videos and take notes and not do any coding. But if you are familiar with coding MATLAB or Python, then I do recommend following along with the code and going through the code challenges and the code exercises. It's really a great way for you to consolidate all of the knowledge that you're gaining here. Okay, so if you want to follow along in MATLAB, you will need access to MATLAB of course, but also these statistics and machine learning toolbox. So to find out if you need if you have these statistics toolbox, you can type VR for version. And that's going to dump out all of the toolboxes that you have available as well as some other information. So if you see these statistics and machine learning toolbox, you are golden. You're good to go. If you do not have the statistics and machine learning toolbox, and it's totally fine, you can follow along in Octave. I'm going to show you that in one moment. I just want to mention briefly that I filmed this course using MATLAB version 2019. I'm pretty sure that everything in this course will work with any other version of MATLAB. If you have any problems getting my code to run with your MATLAB version, post to the Conda and I will help you out. Now some people have access to MATLAB, but they do not have access to the statistics toolbox. If this is you, if you fall into this category, then I recommend using a free software called Octave. It's called GNU Octave. You can find it at, don't you worry about the euro. It's probably faster just to Google for Octave GNU Octave. This is a cross-platform and free software package. It is not exactly like a free version of MATLAB, but it runs nearly all MATLAB commands. So you can run most MATLAB functions inside your Octave installation. So you go to this website, you download it. It's pretty easy. You will need to install the statistics package that's also free. None of this requires any registration or any money or anything. You will need to install these statistics package. That's a separate thing to do through Octave. And I'm not going to provide support for that. But you can look online how to install the statistics package in Octave. It's very easy to do. If you are following along in Python, then I wrote all the code for this course using Jupyter IE Python notebooks, so they look something like this. Now in theory you can follow along using any Python idea you like, so any other environments that you prefer. However, I very strongly encourage you to follow along in Jupyter Notebook installed through the Anaconda package. And the benefit of running Jupyter through Anaconda is that everything you need is going to be installed alongside your package. You don't need to worry about any additional dependencies that you will need to install. So if you do not have the Anaconda package downloaded and installed on your computer, it's very easy to install. It's totally free and it's cross-platform. So you go to their website, anaconda.com. You go to products and individual editions, and they change their website every now and then. So it might look slightly different from what you see here, but it's going to be something like this. Subproducts individual edition, and scroll down. We want to go to download. And here you definitely want to install Python 3, not Python 2. And almost certainly you're going to be using 64-bit and not 32-bit. And of course, there is a Windows version, a Mac version, and a Linux course version with something that is fun and interactive. So what you are going to do is simulate data. You're going to make up some data, generate some data with different parameters that you get to specify. And then the idea is to perform a statistical test to see whether the data that you specified, based on the parameters that you created, whether those two groups of data are statistically significantly different or whether they are not statistically significantly different. So the first step is that you need to download the resources for this video. So there is a resources file. It's a zip file. If you download it, you'll see that zip file contains two separate files. 1 is for MATLAB. It's M and 1 is for Python. It's not IPY and B. If you are following along in this course in MATLAB, then keep watching. If you're following along in this course in Python, then you can skip to the timestamp where I switch to Python. Okay, so you open up the MATLAB code in your MATLAB window. It's going to look something like this. And then here is the idea. We close this window. The idea is that you get to specify the average of the two groups. So group 1 has an average value of 40. Group 2 is an average value of 45. Doesn't really matter what these numbers stand for. You can imagine that they are like the number of jelly beans that people eat in these two groups per day. And then we have the amount of individual variability. And that's the same for both groups. So you only specify this number once. And then we have the sample sizes for each group. So how many people are in group 1 where they eat an average of 40 jelly beans? And how many people are in group 2 where they eat an average of 45 jelly beans? Now, that's all you need to change in the code. That's all the parameters you need to worry about. There's a bunch of code that's, in the rest of this file. You can look through it if you like. That's certainly fine, but you do not need to. If all this stuff looks confusing, then don't worry. That's why you're in this course. But I would like you to do is just change these values and then run the code. You can click on Ed and Run. There's also a keyboard shortcut. If you click inside the script, you can press F5 on your keyboard. So then you see this figure that automatically appears when you run the code, and it will show all the individual data points for group 1 and all the individual data points for group 2. And this is called a violin plot. It shows you the distribution of data points. So it looks pretty nice. So we see that group 1 is a little bit smaller than group 2. And here the title tells us that the two groups are statistically significantly different with a t-value of -0.35 and a p-value of 0.0007. Now, if you are not really familiar with t-values and p-values, then don't worry. You're in the right place. What I want you to do is just focus on changing these parameters and how that affects whether the two groups are going to be significantly different. So, for example, you can make the groups be much further apart. Now it's 40 versus 4 jelly beans. Well, here we get negative jelly beans. So maybe this example wasn't the best thing. So now the groups are significantly different. Let's set them to have a different mean, but much closer together. So now we find that the two groups are not significantly different. So this is pretty interesting. And, there's other things we can try. We can make the variability much smaller. So I'll set that to be 0.6. And now we find that the groups are significantly different. And they really look very different. The scale on the y-axis has changed quite a bit. So there's all sorts of interesting things that you can play around with here. 5 different parameters that you can play around with. What I would like you to do is just spend a few moments randomly poking around these different parameters. Just have fun, explore a little bit. If you make any new amazing discoveries about statistics or about jelly bean eating, then feel free to post to the Conda. Otherwise, the main point of this exercise is for you to just dip your toes into the ocean of statistics, anything that seems mysterious or unexplained. In this exercise are things that I'm going to teach you about later on in this course. As you can see, I go through the Python code in this course using the Jupyter Notebook through the Anaconda environment. So I also recommend installing Jupyter on your computer locally through Anaconda. Okay, so then you can open up this file that you've downloaded from the resources associated with this video. And so the idea here is that we are going to create data. We're going to simulate data. And we're going to test whether those data are statistically significantly different from each other. So this one cell here, this is the cell that contains parameters that you can change. You can see there's a bunch of code in the rest of this file. And these are all things that, if you're curious, you can look through them. But if these lines of code seem mysterious and you're not really sure what a violin plot means or what a t-test and is for, then don't worry. That's the whole point of this course. So for now, all you need to focus on is playing around with these parameters and then scrolling down and you can look at the visualization that results. So let me tell you about the data that we are going to create here. So we create two groups of data. One has an average value of 40 and one has an average value of 45. And then there's a standard deviation. This basically refers to how much individual variability there is, how much the people in our groups are different from each other. And then, here you can also select the sample sizes. So you can make some groups or one group, we have more individuals and one group have fewer individuals, as you like. So these are the parameters that you can play around with. Once you've changed these parameters to some values that you're curious about, you have to run the entire script, and the easiest way to do that, it's just by clicking on this double arrow symbol here and you get a little warning message and you say restart and run all cells. And then you can scroll down to the bottom. And here you see the visualization. So this shows all of the individual data points in group 1. And this shows all of the individual data points in group 2. And then we get this message on top. That tells us in this case, the two groups are statistically significantly different from each other. Now, if you are not familiar with t-statistics and interpreting t-values and what p-values mean, then don't worry. That's the whole point of this course. You're going to learn all of this stuff. What I want you to do now is just, get your feet wet, spend some time playing around with these parameters and see how that affects the resulting plots. And also, the resulting statistical significances. For example, you can try changing these numbers so the average of the groups to be closer to each other. Now, they're not the same, but they're closer to each other. And let's see what happens here. So now in this case, we find that the two groups are not statistically significantly different from each other. And now we can try changing the variability. Maybe I'll set the variability to be 1.6 instead of 5.6. So run this again. No, I haven't changed the averages. I've just changed the variability. And now we find that the two groups are statistically significantly different from each other. So that's already really interesting, because we've just discovered without learning really any of the details about what this test is or how to interpret it, we've already discovered that something about the individual variability is important for detecting significant differences between groups when the average differences are pretty small. Okay, so this is just an illustration of the ways that you can start playing around with this code, and if you make any interesting observations or really great discoveries, and feel free to post them to the Conda. If you take a statistics course with a math professor, your professor will probably tell you that you shouldn't waste your time memorizing formulas. And instead, you should focus on understanding the concepts behind the formulas so that you can always reconstruct the formulas or derive them when you need to. Now, that sounds like good advice. And I'm sure people who say things like that mean well, but the fact is that it's very easy for someone who's been studying and teaching statistics and math for decades to say something like that, because they are so familiar with those formulas that it's almost trivial for them to read or write the formula from scratch. But that is totally different from struggling to learn the formulas for the very first time in your first statistics course. So what do I think? Do I think you should memorize formulas? Actually, yes, I do. Of course, not every single formula needs to be completely committed to memory. But I think it's actually a good idea to try to memorize some of the most important formulas in statistics. And that's because when you memorize a formula, it becomes easier to understand and remember the concept that that formula is expressing. Now, in other cases, I don't think you need to memorize the entire formula per se, but I do think it's worth memorizing the concept or the idea or just some of the key bits of the formula. So as I go through this course and each time I introduce a formula, I will tell you whether you need to memorize that formula or not. Now, some formulas you don't need to memorize because they're worked into analysis software that you actually use in practice to do your statistics in those cases. I show you the formulas to make sure you get the concept and to prevent the case where you might think that the analysis are magical or just really, really complicated. And of course, all the formulas for statistics can be found online or in textbooks in case you ever need to look them up. But there are formulas that I really think are worth committing to memory. And I will try to remember every time I introduce such a formula to tell you which formulas should be memorized, or sometimes you just memorize a little bit. So the key aspects of the formula should be memorized, maybe not necessarily the entire formula, including all of the optional parameters. I think that memorizing important formulas will help you understand how the analysis works. One example is the t-test. I think that if you memorize the formula for the t-statistic, then that will help you remember exactly what a t-test tests for. And I think that memorizing the formula for the t-statistic will help you connect the t-test to other kinds of statistical analysis that have a similar overall structure but are slightly different. You do not need to be a mathematics expert in order to do well at this course. You don't need to have a degree in math. You don't need to have taken advanced university-level courses in mathematics in order to succeed and learn everything about statistics from this course. However, there are some basic mathematical principles that you need to know. And in this section of the course, I'm going to go through those principles a bit briskly. I hope most of this is a reminder for you rather than something totally new that you haven't encountered before. So you do need to know basic arithmetic. I assume that you can interpret these symbols and you can evaluate these expressions. You also need to know some basic algebra like substitutions. So, you know, substituting x for 7 here. And you also need to know how to solve for particular variables. So, for example, if I would ask you to solve this equation for x, you would need to know how to do that. So do you know, divide by both sides of the equation by 3 and then divide both sides of the equation by 4 plus y, and then you isolate x on the left-hand side and have whatever else is on the right-hand side. Now, I don't need to do that here, but just so do you know how to solve that kind of mathematical operation. There's also exponents. That's when you see a smaller, cuter number that is superscripted. So it's above and to the right of what's called the base number. And that just means to repeat multiplication some number of times. So, 3 to the power of 2 or 3 squared is 3 times 3's. We have the 3's twice because there's a 2 here. So 3 to the power of 4 is 3 times 3 times 3 times 3. Then there's something called the law of exponents, which sounds really fancy and dramatic. But it simply means that if you are multiplying two numbers that have exponents in them, then if the bases are the same, like the 3 and the 3, then you can add the exponent. So, 3 to the power of 2 times 3 to the power of 4 equals 3 to the power of the combination of 2 plus 4. So that's just 6 3's written out. Now this only works when the base is the same. So here we have 3 squared times 4 cubed. And it's not possible to combine the 2 and the 3 here because the bases are different. Now, an important use of exponents is putting a negative sign in the exponent, and that's often used as a convenient mathematical shorthand for indicating a fraction. So when you see a negative sign in the exponent, then you take the reciprocal of the base. So n to the power of minus 1 means 1 divided by n. So people often use this kind of shorthand if they basically just want to save some vertical real estate. Here you can see that this is more compact vertically, and this takes up a larger space. So when there's equations that are written in the middle of text, or if there's a lot of space or there isn't a lot of space on the screen, then people will use this notation. I use this quite often, more generally, and to the power of minus a is the same thing as 1 divided by n to the power of a. So you still have to preserve the exponent here implicitly. There's a 1 over here, and the minus sign just means that you take the reciprocal of this number and then you get rid of the minus sign, of course. So that was a quick reminder of the arithmetic, the basic algebra, solving 4 variables and experience that you will need to know for the rest of this course. I think the most important concept here is that when there's a negative sign in the exponent, you take the reciprocal of the number. In this video, I'm going to extend what I discussed in the previous video about exponents to something called scientific notation, which is related to another concept called order of magnitude. So what do these things mean? Well, we can start off by writing that 10 equals 10 to the power of 1. Nothing terribly exciting here. We can also say that 100 equals 10 to the power of 2. And that's because we have the base number 10 and the 2 in the exponent. So we say 10 times 10. So repeat this twice. Multiply them. That of course gives 100. So we can continue this. 1000 is 10 to the 3. 10,000 is 10 to the 4. And 100,000 is 10 to the 5. And of course you could keep going up ad nauseum. And above here, above 10 to the 1 would be 10 to the 0, which turns out to be 1. Now, this may seem counterintuitive. At first you might think that 10 to the 0 should equal 0. But in fact, any number to the power of 0 is equal to 1. So it's just a little quirk. You just have to memorize that. So this was all 10's 4 powers of 10. And these are called orders of magnitude. So the order of magnitude of a number is basically the number in the exponent here. So 1000 is 3 orders of magnitude. 10,000 is 4 orders of magnitude. So you can also discuss relative orders of magnitude. So 10 to the 3. Or let me say it this way. 1000 versus 10,000. Those two numbers are 1 order of magnitude different from each other. So 10,000 is 1 order of magnitude greater than 1000. And that's because when representing these numbers, using exponents like this, 4 is just 1 unit, 1 integer above 3. Okay, so that's all 4 tens. What if we say 200? Can we follow this same pattern and say 200 equals 20 to the power of 3? I probably meant to write 20 to the power of 2 here, but it doesn't matter because it turns out it's wrong. Either way you write it, 200 is also not 22 the power of 2. So I think this was a typo. Just imagine that 2000 and equals 20 to the power of 3. Well, it turns out that that's still wrong, no matter how you put the zeros of the exponent here. So instead, when dealing with numbers other than ones and zeros, like this, we use something else called scientific notation. So we would express 200 as being 2 times 10 squared. So we have 10 squared. That gives us 1 here. And then times 2. And that gives us 200. Likewise, sir. Okay, so now I'm just writing it out. Likewise, you can say that the Number 240 is equal to 2.4 times 10 squared. Again, we have 10 square. That gives us 100 times 2.4 gives us 240. Now, when you look at a simple example like this, you might think, well, come on, this is pretty ridiculous. This is only 3 characters here we have so many more characters. This is so much more complicated. And it's true in this very, very simple example, it's better to use 240 than 2.4 times 10 squared. But for larger numbers and in particular for comparing numbers of different magnitude, this is called scientific notation and it's useful for working with a larger range of numbers. Now on computers, so if you're writing this out, you would typically do something like this. Computers will often replace the times 10 with e. So on a computer, you might see something that looks like this, 2.4e2. And this actually means 2.4 times 10 squared 10 to the power of 2. And of course, in this case, that's equal to 240. And just like what I explained in the previous video on exponents with having a negative sign in the exponent, you can have 2.4 times 10 to the minus 2. And that actually equals, well, what does it equal? Let's think about this. If there's a minus sign here, does that mean we take the reciprocal? And if this was 2.4 times 10 to the minus 2, does that mean 1 divided by 240? Actually, it doesn't have to be careful here. We're not taking this number to the power of minus 1. It's only this number to the power of minus 1 or minus 2. So, in fact, it's 2.4 times 10 to the power of minus 2. So if there were a minus sign in here, then basically what you're doing is moving this decimal point over 2 places. So 2.4 times 10 to the minus 2 is the same thing as saying 0.024. And using this notation on computers, you would see e minus 2. So this would say 2.4, e minus 2. You'll see this very often in computers when we start working with p-values and very small numbers. So you might have a number 0.00009436. Whatever. And then the computer is going to represent that as 9.3 or whatever number. I said 9.3 e minus 6. So that's basically just going to be a very, very small number. So in this video, I introduced you to orders of magnitude and how to write a number. And how to interpret numbers in scientific notation. This is something you see quite often when working with very large numbers and very small numbers on computers. The summation notation is super important in statistics. You will see this notation all over the place in statistics, certainly in this course. So if you are not already comfortable with these summation sign, then definitely put your thinking cap on for this video. Okay, so let's start with a set of numbers. I call this set A and it's just this list of 5 numbers, so we can ask what is the sum of all the numbers in this set? Well, it's pretty trivial to compute. It's just 1 plus 3 plus 4 plus 1 plus 6. And according to my genius mathematical computations, that equals 15. You can break out your super fancy calculator and confirm that I've gotten the right solution anyway. So this is fine for this little problem. But what if we had a larger number of numbers, or what if we don't even know exactly how many numbers? Or maybe it doesn't matter exactly what these numbers are. We want to express the sum of all the elements in this set. Well, we could also write it out this way. So you have a subscript 1 plus a subscript 2. So the subscripts would be indicating the indices. So this is the first element of A. This is the second element of A, which is the number 3. And then you have this dot, dot, dot. That's the ellipse. This indicates in math that there's a bunch of stuff missing in here that We're not printing out up to the nth element of A. Now, this is a slightly better way to write out the summation compared to this, because here we don't need to know, or I should say this expression generalizes to any number of elements in A. So however long A is, and it also doesn't matter exactly what the elements are. And we can get even better than this. We can write even better, more compact notation. And that is this summation notation. So it's this biggie looking thing. It's actually the Greek capital letter sigma. And this indicates a summation. So the way that you read this expression here is actually a little bit like A for loop in computer code. So, you say for I equals 1 until I equals n, so basically, we're looping through indices. This would be the 8th index from the first index up to the nth index of A. And then what do? We just sum all of the elements of A. So this compact notation is the same thing as this. And for this specific example, this notation is also the same thing as this expression here on the left side of this equation. So you can see this is a really compact and handy way of writing out the summation of all the elements in some vector or some set of numbers. And of course, this can be more complicated. Maybe it's the, 8 times the index of A times the i's index of B plus 47 to the power of pi, whatever. You can have more complicated expressions inside this summation. The last thing I want to point out here is sometimes you will also see this expression without any of the super subscript or superscript here. And when you see it like this, then, well, technically there's information that's missing. And you just have to do a little bit of guesswork to try and figure out what is the appropriate range of indexing here. And if it's not indicated, then you can generally assume that the index goes from 1 to n, so from the first element in the set up to the last elements in the set. This notation is usually used when there isn't a lot of space in the equation. So then they will just leave these things under the assumption that you know what they're referring to. Okay, so in this video, I covered these summation notation. If that was new information for you, then please take a moment to study it and make sure you understand it. It's going to come up very, very often throughout this course. You are probably already familiar with the concept of the absolute value of a number, but I'm going to give you both a bad definition, which works some of the time, and a much better definition that generalizes to all kinds of numbers that you might encounter in the future in math. So here is a bad way of explaining what the absolute value means. So we could say, and this is something you might have learned, when you were in elementary school, that the absolute value of a no means to strip off the negative sign if it has a negative sign. So you have the absolute value of -4. You just drop the minus sign in. The absolute value is 4. Now, the thing is that works sometimes for real numbers. That actually does work. But that's not the best definition. It's not the best way to think about the absolute value. A better explanation is that the absolute value of a number is the distance of that number to the origin of the number line. Now, these two explanations are compatible for some types of numbers, but they are incompatible for other types of numbers. And this is always the correct explanation, is always the correct definition, and not necessarily this one. So for real numbers, we think of real numbers as being on a line with 0 in the middle. So the absolute value of the number 2 is the distance away from the origin, which is 2 units. Likewise, the absolute value of -5 is 5 because the distance from -5 to the origin is 5 units. Now where the definition of just dropping them minus sign breaks down is when you are working with complex numbers where you have a real part and an imaginary part. You don't have to worry about that in this course. We're not going to be working with or incorporating complex value numbers in this course. Nonetheless, I think it's useful to have a more accurate definition of the absolute value, which is also applicable to other kinds of numbers. There are two kinds of notation for indicating the absolute value of a number. You can see. So when you do like chalkboard math, if you're writing math down in pen and on a piece of paper, you're likely to see this notation where you have these vertical bars surrounding the number, or in this case, the variable. You might also see it written up ABS for absolute value, and then in parentheses, the number or the variable that you're taking. The absolute value of this notation is how it would look in computer code. And this is probably how it would look in the slides or, in a math textbook. So, quick video, I introduce you to absolute value. And I hope it was a good reminder of a bad definition of absolute value and a more accurate definition of absolute value. In this video, I'm going to introduce you to two important and related mathematical functions. And those are the natural exponent and the logarithm. These are actually intimately related to each other. And I will show you that these two functions are inverses of each other. Now, we could spend, if this were a math course, we could spend hours talking about the intricacies of the natural exponent and the natural logarithm and logarithms to different bases. But in this video, I'm going to focus on a more visual and intuitive understanding. Now, before I begin, I want to first discuss some notations which can make things a little bit confusing, and mea culpa. I must admit that I also am occasionally mixing it, certainly in this video and probably in other videos, occasionally mixing these two notations. And while I apologize for making that a little more confusing, but, that's just how it goes when you're integrating math and coding. Okay, so we have this as the notation for the natural exponent in math notation. It's e to the x, and in code it's express and then in parentheses x, so these two are comparable. This is MATLAB code. Of course, if you're doing this in Python, then you just add an MP, right? So this would be numpy.express. So that's not too confusing. It starts getting confusing with the logarithms. So in math notation, the logs to different bases are indicated as the word log. You write out log and then in subscript add letters the base. So this is log base 10 in code, it's log 10. So that part is actually not confusing. What is confusing is that the natural log in math notation is indicated as ln, but in code it's still just log. So this is actually the natural logarithm. This is equivalent. These two expressions are equivalent. This is just a commonly used shorthand in math which has the same meaning as log base e, so you will see in the slides in this video that I sometimes write out log of x when I'm actually referring to the natural log. So whenever you have the word log without any numbers after it or a subscripts after it, you can assume that it is log the log base e, which is the natural logarithm. So a little bit about notation there. So here you see a plot of y equals e to the x. So we have x on the x-axis. And the y-axis is the function e to the power of x. So this is an exponentially increasing function, is why it's called the natural exponent. And there's a couple of important properties of e, so the natural exponent that are worth committing to memory. First of all, this letter e, it stands for an irrational number. So it's a number that never ends. And it is 2.78 something. Something. So a few things to note about e to the x. The function e to the x1 is that it is never negative. It never gets to be a negative number. And furthermore, it never even gets to be 0. it gets very, very, very close to zero, arbitrarily close to zero. On computers, it becomes indistinguishable from zero with some precision errors, round computer rounding errors. But in theory e to the x never actually gets to be zero as x goes to minus infinity. On the plus side, when x goes positive, e to the x goes really, really large. Really, really fast. It blows up to positive infinity very, very quickly. And it's also interesting to keep in mind that when x equals 0 e to the x equals 1. And that's because, as I mentioned a few videos ago, any number to the power of 0 is 1. So this function so y equals 1 when e to the x or for e to the x where x equals 0. So each the x basically grows really, really quickly. Now e to the x, the natural exponent, appears all over mathematics and all over applied mathematics. You see it in growth curves, you see it in finance, you see it in navigation. You see it in trigonometry. As many interesting properties, including, for example, that the derivative of e to the x is also e to the x. Now a lot of these more advanced concepts for e natural exponent are not relevant for us. Now, the important things that you need to know for this course is that e to the power of something. So e to the x is a non-negative function and it very, very quickly blows up to 2 plus infinity. And then we have, it's kind of like the evil twin brother of the natural exponent, which is the natural logarithm. And it almost looks like, it looks a little bit like you just flip this function over like you're just, mirroring or reflecting this function. So this function log x, natural log of x, actually does become negative. In fact, it quickly goes down to minus infinity as x approaches 0. Now x here, I cannot say the function here is not defined for negative values of x, so you cannot take the logarithm of a negative number. That doesn't make any sense. You just get minus infinity or minus not a number. I forget which one. And the log of x on the positive side. As x continues to grow larger, this does creep up to infinity. It just keeps growing. But you can see, it's growing slower and slower. So the larger x becomes, the more slowly log of x will grow. Now, in statistics, log of x, the natural logarithm, is often used to describe differences in probabilities between very small numbers, and you can see why that's the case. So imagine you are trying to distinguish between of two probability values that are very close to each other, maybe 0.01 and 0.02. Now those numbers are very close to each other, but the logarithm of those numbers is further apart. So I will discuss this later on, I think maybe even in the next video. But the logarithm is very useful for distinguishing between very small numbers that are very close to zero. Positive numbers. Now, one interesting thing about e and log, so the natural exponent and the natural logarithm, is that there are perfect inverses of each other. So that means that you can use them to basically negate each other or to cancel each other out here. You see an illustration of that. So if we would plot y1 by y to where y1 is defined as the logarithm of e to the x, and y2 is defined as e to the logarithm of x, for x goes from basically just a little bit above 0 up to 10. Then it turns out that we get a straight line here, and the reason why we get a straight line is because the log undo is that the e or inverts the e, and the e inverse or undo is the log. So in fact, this is really just saying, the log of e to the x is just x and e to the log of x is just x. So in fact, what we're doing here is just a bizarrely complicated way of saying plot x by x, which of course is just a straight line. So in this video I introduce you to the intuition of natural exponent and natural logarithm, and I show that these are inverses of each other. Again, logarithm is something you see very often in statistics and machine learning, in particular for optimization of numbers, probability values that are very small. This is going to be a really fun and exciting video. We're going to get to solve math problems and see how two seemingly unrelated expressions in mathematics are actually really closely related to each other. So I hope you're excited. The first thing that I'm going to introduce you to is a function called the sigmoid. This is a function for a sigmoid. We have 1 divided by 1 plus e to the minus beta times x, so x is our function variable. You can just think of it as you can think of it as time or space, doesn't really matter. It's just some sort of continuous number. And beta is a parameter here. So we can look at this in algebra. But this is also pretty easy to graph because it's a function of one variable. So the sigmoid function looks like this. We see here is x on the x-axis. So that's this value here. And then this is the function value on the y-axis. So they call it a sigma because it looks a little bit like an S in some literatures. It's also called an S-curve. In other statistics literatures, I've heard this referred to as a hill curve because it looks kind of like the upslope of a hill. But the formal term is a sigmoid. You can see it goes from 0 to 1 and it kind of climbs up slowly, or smoothly, I should say. Not necessarily slowly. Now, this function is not necessarily bound between 0 and 1. You can imagine multiplying this or having in the numerator a 4 instead of a 1. And then if this were a 4, then this function will actually go from 0 up to 4. And then we could, for example, subtract 2. And then we would have a sigmoid that goes from minus 2 up to plus 2. So there's some ways to parameters this to have this stretch beyond 0 to 1. Now, this beta parameter here turns out to be a key parameter. It's sometimes referred to as the heat parameter or the temperature parameter because it defines the steepness of this incline. So beta, this parameter beta here, will tell us how steep this function climbs from 0 up to once, or whether it's a really steep curve, like almost like a step function, or whether it's really gradual, basically like a linear function with just a little bit of bend to it. All right, so that's the sigmoid function. Now, why am I telling you about the sigmoid when the title of this video is the logistic function? And anyway, what is the logistic function? Well, this is the logistic function. It's the natural log. So in the previous video, I talked about the natural log and I spelled it out log. But another way to refer to the natural log as opposed to a logarithm with some other base is L, and so the natural log of all of this business goes inside the natural log function p divided by 1 minus p, so p here is a probability value. So it varies between 0 and 1. It cannot be negative and it cannot be greater than 1. So the log natural logarithm of p divided by 1 minus p equals beta. So this is called the logistic function. It's really important in odds ratios when learning about probabilities and odds. It's also important for something called a softmax function, which is used in machine learning and in artificial intelligence and reinforcement learning and in deep learning. You will learn more about where this formula comes from and how to work with it in the section on probability theory. So a bit later in this course, what I want to do now is just focus on the math. So here's what you should do. Pause the video and solve this equation for p right now is solved for beta. We want to solve for p. So do whatever you need to do to get this equation to be rewritten so that p is isolated. The probability value is isolated on one side of the equation and everything else is on the other side of the equation. Okay, after you've finished, it's a little bit of a challenge. But you can use some of the knowledge that you learned in the past several videos. And when you've finished or when you've given up, I guess then unpause video, come back and I'm going to work through this solution. Alright, so how did it go? Did you manage to solve for p? Let us start by getting rid of this logarithm. And remember, from the last video, the way that you get rid of the logarithm is by taking e using the natural exponential. So we take e to the all of this business. And of course, whatever you do to one side of the equation, you have to do to the other side of the equation as well. Now, when that expression gets pretty complicated and you want to put the entire thing in the exponent, it's common to write exp for natural exponential and then whatever is in parentheses is actually in the superscript. It's actually in the power of e. Okay, so now we know that e and log cancel each other out. So these two operations invert each other and we get p over 1 minus p equals e to the beta. So we're not finished yet, right? Because we need to isolate one p on the left-hand side of the equation. So, let's start by multiplying both sides of this equation by 1 minus p that gives us this. But we still have a problem because we need to get these to piece together basically on one side. Okay, so what I'm gonna do now is up here, expand out this multiplication and then things are starting to get pretty interesting. Now what we can do is group together the two terms that contain the probability on one side of the equation and put the e on the other side of the equation. So, that's what I've done here. So now we have the sum of two terms each, both of which have p in them. So we can pull that p out. And then we get e to the beta equals 1 plus each of the beta times piece. So now things are going well. We have only one value of pure one instance of this probability term over here. So of course we divide by e to the beta. And I just swap the size here. So on the one hand, this is fine. You could stop here. This is technically, the solution. But it's a little bit ugly to have e to the beta in the numerator and each of the beta in the denominator. So what can we do here? Well, we can do is multiply this expression by e to the minus beta divided by e to the minus beta. Is it just a little trick that we're using here? Now this is equal to 1, except normally when you're doing something like this in math, you have to be careful. Now, when you're introducing something into the denominator, you need to think about whether that can ever be 0 and therefore whether you need to make some exceptions or some assumptions built into your ultimate solution. However, remember, from the last video e to the anything can never be 0. This can never be 0. Can get really close to 0. But we don't have to worry about dividing by 0. Okay, and then we apply the law of exponents from several videos ago and these bases are the same. So we can add the exponents here. And so beta minus beta is 0. So we get in the numerator e to the 0, which you'll remember is 1. And here we get e to the minus beta over here. So we're multiplying this entire denominator. So we get e to the minus beta. And here again, we get e to the beta minus beta, which is each of the 0, which is 1. And that gives us our final solution. That's the probability piece. That's how to solve the odds ratio here in this logistic function. For p is p equals 1 over 1 plus e to the minus beta, which is really cool because that's exactly the sigmoid function that I showed in the previous slide. Well, not exactly, that one had an x there. But so this is just being evaluated for one particular value of x, alright. So in this video, I introduce you to the logistic function and the sigmoid function. And you got some experience. using a little bit of paper and pencil math to work through using natural exponent and natural logarithm to solve for probability values. That turns out to be pretty important. When we get to the section on probabilities,